Okay, AP Calculus students, we are going to continue working on 4.2, area with summation, and the Fundamental Theorem of Calculus. For our first example, I'm asking you to evaluate the following limit as n approaches infinity. To do this, we're going to have to repeat writing this limit here as n approaches infinity numerous times. The first thing that I notice is that this 2 over n here is a constant. So this 2 over n is going to come out and go right in the middle here between my limit as n approaches infinity and my summation. So I am going to write that with a 2 over n multiplied by the summation as I goes from 1 to n, big bracket. And within this step, I'm going to FOIL out my 5 plus 2i over n. This is going to give me 3 multiplied by, if I take 5 times 5, I get 25 plus 5 times 2i over n is 10i over n, and I'm going to have that term twice, so that doubles that and gives me 20i over n, plus 2i over n quantity squared is 4i squared divided by n squared. Close my parentheses, and I will multiply out the 2 to the 5 plus 2n, yielding 10 plus 4i over n. Close my bracket. Okay, we're going to clean this up a little bit. This is still the limit as n approaches infinity of 2 over n multiplied by the summation as I goes from 1 to n of, and we are going to multiply out this 3, giving me 75 plus 60i over n, and then plus 12i squared divided by n squared, plus 10 plus 4i over n. Now clean it up again, combine like terms. We are looking at the limit as n approaches infinity of 2 over n multiplied by the summation as I goes from 1 to n. Let's see what we have. 75 plus 10 is 85. 60i over n plus 4i over n is going to give us a positive 64i over n. And then the 12i squared over n squared stays right where it is. Okay, next step is actually one last summation property, which means we are going to distribute that summation and apply it to each of the 3 terms inside. So I am looking at the limit as n approaches infinity of 2 over n multiplied big bracket here. This is the summation as I goes from 1 to n of 85. And I don't think that n looks very nice. Looks kind of like an H, doesn't it? Plus the summation again as I goes from 1 to n of 64 over n multiplied by I, and then plus the summation as I goes from 1 to n again of, let me wrap that in parentheses, wrap this in parentheses, 12i squared, well, you know what, let's call this 12 over n squared multiplied by I squared. Close my bracket. Now one more step to clean this up is to take my constants to the left of the summation, with the exception of the 85. I want to leave that right where it is just because I like the looks of it right there. This is the limit as n approaches infinity of 2 over n multiplied by the summation as I goes from 1 to n of 85, plus I'm going to take the 64 over n outside of my summation as I goes from 1 to n of I. There's a formula that I can use for that. And then plus the 12 over n squared will get factored out, multiplied by the summation as I goes from 1 to n of I squared. And you can see my formulas are like right in your face there for the last 2. Okay, continuing along here, what do we have? We're still looking at the limit as n approaches infinity of 2 divided by n, open bracket. Now this formula here just says the summation as I goes from 1 to n of any constant is that constant, 85, multiplied by n. So that was my formula. I just executed that formula. I'm going to copy this 64 over n here, and now I have a formula for the summation as I goes from 1 to n of I. And that formula is simply multiplying by n times n plus 1, all divided by 2. You can review your formulas, but that definitely is the formula for that. More multiplication here. Plus 12 over n squared. I'll wrap that in parentheses just to keep the same format that I have here. You know what? I'll take that dot out of there. Put that like that. And here we go. The summation as I goes from 1 to n of I squared is n times n plus 1 times 2n plus 1, all divided by 6. Close my bracket. And now my job is to write this with the least possible number of n's before I evaluate my limit as n goes to infinity. Let me see, equals limit as n goes to infinity. I can clean this up right now, or I can distribute the 2 over n at the same time. I bet you can handle it. Let me see. Let me just write this. 2 over n multiplied by 85 times n plus 2 over n multiplied by 64 over n multiplied by n times n plus 1 divided by 2. And I suppose if I wanted to follow formatting, I can do this. You know what? Let's do that. Plus, over here on the end again, my 2 over n is getting distributed inside this bracket, multiplied by 12 over n squared, multiplied by n times n plus 1 times 2n plus 1, all divided by 6. That is my formula there. Wrap that up in brackets. And now that my distribution has happened, I need to simplify things down as much as possible. So this gives me the limit as n approaches infinity. And you know, the more intuitive you are, the faster you can get this process done from here. So I'm just going to take my time, but I'll talk to you about it in just a few more minutes. My n's divide off here and here, and then 2 times 85 is going to give me 170, plus I have a 2 down in my denominator and a 2 in my numerator, so those are going to disappear. I have an n down in this denominator and up that numerator, those are going to disappear. And I'm just going to have a 64 multiplied by n plus 1, all divided by n for that particular term. So plus, let's see here, I see a 6 on the denominator, so I'm going to take 6 into 6 once and 6 into 12 twice. I see this n over here once, I see this n once. So everything looks like it's pretty well broken down. I have 2 times 2 giving me 4 on the numerator, n plus 1, 2n plus 1, and on my denominator the only thing left there is n squared. So that seems like it's broken down quite nicely. Now we can take our time, or we can jump ahead a little bit here and see what's going on. The limit as n approaches infinity of 170 is just 170. So I'm just going to, I've been taking my time all the way through this thing. Let me see. I think I will, yeah, I'm jumping. I'm sorry. But the limit as n approaches infinity of 170 is 170 because there's no n there. Plus, I want you to realize that the degree of this numerator right here is a 1, and the degree of the denominator is a 1. So therefore, when I'm trying to evaluate the limit as n approaches infinity, what I'm doing really is looking for any horizontal asymptotes for this particular term as a function. So since the degrees of the numerator and denominator are equal, I take the ratio of the leading coefficients. The leading coefficient on my numerator is simply 64, and the leading coefficient on my denominator is a 1, so I just get 64 out of that deal. Plus, again, I'm looking for the limit as n approaches infinity here. I have a polynomial function on my numerator, a polynomial function on my denominator that gives me a rational function. I am looking for the degree of the numerator. Hopefully you can tell that this is a 2, because this is n to the first here and another n to the first, which means if I were to multiply this whole numerator out, I would end up with 8n squared, which tells me that the 2 would be the degree of the numerator. We can clearly see that the 2 is the degree of the denominator because it just says n squared. So once again, when the degree of the numerator and the degree of the denominator are equal to each other, we take the ratio of the leading coefficients. The leading coefficient on my numerator would be 4 times 2, giving me 8, and the denominator has simply a 1 sitting here just like this did. So 8 compared to 1 is just 8. I add 170 and 64 and 8 all together, and I end up getting 242 for my final answer. And that is what the limit of that whole summation is equal to. Okay? Now, I would like to address the same question in a slightly different manner. Knowing what I know, I'm going to recreate something. So let me take this away, and put my bracket back on. I'm going to take this question one more time, which says evaluate. Let me see if I can get it all. Hopefully I can. And I'm going to copy that. I'm going to come down here and paste this question one more time. Very good. All right. So this is example 1. We're just going to do it a totally different way this time. All right, I'm going to look at this function and I'm going to try and decide if I can figure out what the function itself was. I know that this is looking right here. This piece of the puzzle right here is my f of c sub I, and I know that this piece of the puzzle right here is my delta x. So I know my delta x quickly is 2 over n. That really makes good sense to me. Not quite sure how to play with that yet until I see a little something else. Now the c sub I, first off, can you tell me what the function is before I talk about the c sub I? Can you tell me that something got substituted into this? Oops, I'm sorry. Doesn't it look like we had an oogie boogie that I put into those parentheses if that were my given information? So the function itself, f of x, would be 3x squared plus 2x. You have to be able to notice that from this information up in the beginning here. This right here, this 5 plus 2y over n, you can see it's repeating itself, so that is definitely what got substituted into the original function, and that is going to be my c sub I. So let me write that down as well. This is my c sub I, this is my c sub I. And I know that my c sub I is a plus I delta x. And since the c sub I right there is given as 5 plus 2i over n, it follows that the a is going to equal 5. It's pretty simple. Whatever that first number is, that's where you're starting on your interval. So my a is definitely equal to 5. And look over here where I told you that delta x was 2 over n. If delta x is equal to 2 over n, and I see a 2 over n right here, doesn't that make sense? Doesn't that connect? Doesn't that make good sense that the 2 over n is the delta x right here that got multiplied by I, and then we just turned it around, and instead of writing I delta x, it looks more like delta x times I. So hopefully that makes good sense to you. Now this delta x has a formula. Let me see, 2 over n. Delta x has a formula as equaling b minus a over n. So if b minus a over n is the formula for delta x, well then b minus a over n has to equal 2 over n. My denominators match, therefore my numerators must match, and I know that b minus a has to equal 2. I have my a is 5, so I'm going to bring a 5 over here. I now have b minus 5 equals 2. I add 5 to both sides, and I now know that my b is 7. That gives me my interval. AB is now my interval from 5 to 7. So that should make pretty good sense to you. I'm hoping it makes pretty good sense to you. All right. Well, as long as you can recognize the limit formula with the summation of the height times the base, you will realize that we are doing an infinite sum for the area of an infinite amount of rectangles. We are looking for the area bounded by the curve or the function of f of x equals 3x squared plus 2x. The line x equals 5, the line x equals 7, and of course the x-axis, which I could call y equals 0, but I'm just going to call the x-axis. According to the Fundamental Theorem of Calculus, that is the same thing here as the integral from a to b of f of x with respect to x, which is equal to the integral from 5 to 7 of 3x squared plus 2x with respect to x is dx. See how this is kind of still my f of c sub I, delta x. Still follows the same format. Okay, I'm just going to erase that piece. Very good. Okay, fundamental theorem of calculus says go ahead and integrate this. So when I integrate 3x squared, I simply get x cubed. And if I integrate 2x, I simply get x squared. I'm going to take that and evaluate this function from 5 to 7. So big bracket, something cubed plus something squared, close my bracket, minus, open bracket, something cubed plus something squared, close my bracket. What goes into the first set of brackets? Your upper limit, which means 7 and 7. And what goes into my second set of brackets should be my lower limit, which would be 5 and 5. Set your brackets up, make everything nice and neat so you don't accidentally put 7, 5, 7, 5. That would be a big no-no. Alrighty, simplify inside your brackets first. 7 cubed, trust me on this, is 343. 7 squared, trust yourself on that, is 49. Minus 5 cubed, giving me 125, plus 5 squared is 25. 343 plus 49 yields 392, and 125 plus 25 yields 150. Since they're the only things now left inside those brackets, I don't need my brackets. You can go to the side if you wish, but 392 take away 150 is 242, which gives me the same answer that I had way up here when I did the whole limit process out altogether. Let's see, 242 right there, doing the long limit process out, and noticing the limit process as being an integral question, and implementing the fundamental theorem of calculus, integrate and evaluate from your top limit, subtract your minus limit, you get this, or subtract your lower limit, sorry, you get the same 242 both ways. Okay? So I'm going to leave it at that. That is the end of this particular example. Okay? So, Talon out. Whoop, whoop. Talon out.